In this video I'm going to simulate the simple logic gates that we're going to use throughout the CPU design. I'm also going to show you how we can create these simple logic gates using just the NAND gate. So let's get cracking and let's get this done. We could design the entire CPU using just the NAND gate. So I could change this NAND gate in order to generate an AND, an OR, a NOR, exclusive OR and exclusive NOR. So let's give a wee look and we'll see how we can do that. So if we simulate the NAND gate first of all, we'll put our two inputs in, and I suggest you go ahead, if you've got the tool there, and go ahead and try this for yourself. So we'll run the simulation. We can see that when both are low, that output is high. When that is high, the output is high. When that goes high, the output is high. When both are high, the output goes low. So you can see the truth table for that if you get into Analyze Circuit. And there's the expression there. So we only get a low output whenever both inputs are high. Otherwise we get a high output. Now we can use this truth table in order to generate the rest of the basic logic functions. And let's go ahead and we'll do that now. So first of all, we can change this NAND gate into a NOT gate, and we can see from the truth table how we're going to do that. If we went into Analyze Circuit, and this is a truth table for our NAND gate. Now if we were to notice that whenever both A and B are 0, we get a 1 output, and when both A and B are 1, we get a 0 output. So that's really what a NOT gate does. It takes a 0 and gives us a 1, or takes us a 1 and gives us a 0. We just have to make sure that these two states, the 0, 1, 1, 0, don't occur. Well, that's easy enough. We just make both of them equal to each other. So how do we do that? Well, that's simple. All we do is just connect them together. So we connect that together. Then we've got a NOT gate. So let's just check and see if that actually works. So a 1 gives us a 0, and a 0 gives us a 1. And again, you can get in and look at the Analyze Circuit, and you can see there that we've turned our NAND gate into a NOT gate. So let's look at another one. Now we can generate an AND gate from the NAND gate by inverting the output. But we know how to invert the output. We can just use this little NOT gate here. But we've already designed a NOT gate using an AND gate. So we can go ahead here and we can produce this NOT gate here, and we can connect this to our output. So what we should have here now is an AND gate. So let's go ahead and see if that's what we have. If we've got 0, 0, we've got a 0 here. If we make that high, nothing happens. Make that high, nothing happens. Make both of them high, then we get an output there. So this shows us that we've created an AND gate using two NAND gates, and we can see that in the Analyze Circuits, and we can see that we only get an output when both A and B are high. So let's go ahead and we'll have a look at another one. So we can create an OR gate from 3 NAND gates, and that's the realization there. So we simply have a NAND gate, and these two NAND gates are connected together as inverters or NOT gates. So if we invert the inputs, we can create an OR gate. So this thing here is just the same as one of these. Okay, so let's go ahead and we'll just check that, make sure it is actually working. If I make both of them 0, we get a 0 output. So if I make one input high, we get a high output. Or if I make the other output high, we get a high output, and if we make both of them high, we get a high output. So that there is the realization of an OR gate. So let's have a wee look and see this and make sure we've got it right. So here's the truth table for an OR gate. So we get an output if A or B or both are high. So let's go ahead and we'll look at another little circuit. So we can create a NOR gate now simply by inverting the output. So I could take another one of these NAND gates and tie the two together and put it as an output, but we don't need to. We could just put in this realization here. It's the same thing. So we could put this in here. So now we've got a NOR gate using what would be 1, 2, 3, 4 NAND gates. So let's go ahead and we'll check and see whether this actually works. So if when both inputs are low, we get a high output. When one is high, we get a low output. When that other one's high, we get a low output. When both are high, we get a low output. So that's the NOR realization. You can see that in the truth table. So there's a little truth table there. So we only get a high output when both inputs are low. And that's in effect the opposite of the OR gate. So let's go and have a look at another one. So this is our realization for an exclusive OR. So we can build an exclusive OR using 1, 2, 3, and if those are replaced by NAND gates, that would be 4, 5 NAND gates. So let's go ahead and we'll check and see that actually works. When I've got 2 zeros in the input, I've got 0 in output. When I've got a 1 in the input there, I've got a 1 in output. When I've got 1 in input, I've got 1 in output. And when I've got both 1s, I've got a 0. So that's called an exclusive OR. And we'll see the truth table for that now. So this is the truth table here for an exclusive OR. We only get an output if either A or B is high. And if both are low and both are high, we don't get an output. Of course, we could create the exclusive NOR simply by inverting this output. So we could delete this off and stick in another inverter, and it would give us an exclusive NOR gate. And we can see that if we were to look at the analyzed circuit. And this here would be an exclusive NOR. But it's not a very efficient way of doing this because we're going to be doing it with 1, 2, 3, 4, 5, 6 gates, and you can do it with 5 gates. So I'll leave that up to yourself, and you can work out the realization for a 5 gate exclusive NOR if you're interested. Of course, you can also just go up to Google and Google it if you want as well, and go build it up. So we can create all our basic logic elements just using one single logic type, which is the NAND. Now we could also do this with the NOR gate as well. So it shows that we're able to build up an entire CPU if we would want to, just using one gate type, either the NAND or the NOR. My original intention was to go through the entire CPU design just using the NAND gate. Now I decided against that for a couple of reasons. The first of them was purely aesthetic. Whenever I created the gates, my drawings for the gates would probably be less tidy than the drawings you have here. So I decided for that reason that I would stick to just the gates that they offer here. But more importantly, whenever we run Logisim to create the CPU, we're really running it at its very limits. And if I can cut down the number of gates, then it makes the simulation run a bit better and run a little faster. So that was part of the reason as well why I decided not to design the whole thing in NAND gates. So I hope this video was of use to you. It's just a little add-in to get used to using the tool, and also to get used to some of the basic gates that we're going to be using throughout the rest of the design. So I'll get you on the next video. Goodbye.